So the question we are going to do now is again a very popular question, and it has a very huge practical application, and it was once asked to one of my juniors in his Amazon interview. So it is a very interview specific problem as well. So it says that you have been given an array. Let's say the array contains 10, 20, 15, 2, 33, 90, 67. Okay. So this is what my array is. Now I define a particular kind of element. I call that as peak element. Okay. So I'll define peak element for you. Peak element is such an element a of I such that a of I is greater than equals to its left also, and it is greater than equals to its right also. So if there is an element which is greater than equals to its left also and greater than equals to its right also, that element will be called as a peak element, right? Now tell me one thing. In my array, there can be certain elements which do not have their left, and similarly there can be some elements which do not have their right, isn't it? Like the first element will not have left and the last element will not have right. So in that case you just need to compare a of I with ai plus 1 if I is 0. Similarly, if I is n minus 1, then you need to compare ai with ai minus 1. So you basically compare with the left and right only if they exist. If one of them do not exist, you do not compare with that. So by that I mean that if, let's say, my last element was 670, would I say that this is a peak element? Would I say that 670 is a peak element? Yes, because it is greater than its left. The right one doesn't exist, so I do not compare with it. Okay, cool. Now tell me one thing, can an array have multiple peaks? Can an array have multiple peaks? Yes, no? Yes, very well. It can have multiple peaks, right? Yes. So if you understand it, then tell me what are the peak elements in this case? Which elements of the array are peak? Can I say these are the two peak elements? Yeah, they are the two peak elements. So the question is simple. Question says that return any one peak element. I am not interested in which element you return. You return any one peak element. Whether you return 20 or you return 90, it is okay to me. But it should be a peak. So if you understood the problem, then think how it can be solved. And as I said, now here the array can be any random array. It is not sorted array, it is not sorted rotated array, it is just a random array. So then think how you can maybe think of an efficient approach over here. Yeah, linear search. Can all of you do it using linear search? All of you can do it using linear search, right? In order n time. But that is order n. So think, can you optimize? Can you do it in order log n time? Something like binary search. So listen to it very carefully, because I already told that this question has practical applications. Guys, tell me one thing. Can I say that any random array that I have, I don't know how it looks like, any random array that I have will at least have one peak? Can I say that? Think before you answer. Can you think of certain arrays that will have no peak at all? Yeah. So think of it in this way. If my array is sorted in ascending order 10, 20, 30, 40, it is sorted in strict ascending order. Strict ascending means increasing, not even equal. What will be answer in this case? What is the peak element in this case? The peak element in this case is 40, because this is the only element which is greater than its left, and right doesn't exist. Let's say it was sorted in descending. If it was sorted in descending, then what would have been my answer? Again 40, because this is the only element which is greater than equals to its right. Okay, so if array is sorted in ascending, then the last element is answer, and if sorted in descending, then the first element is the answer. I believe all of you got it. Now let us try to understand one thing. So what I am going to do is, I am going to plot these graphs on plot these points on a graph. Okay, yeah. So index wise, so this is, let's say, my index 0, index 1, index 2, index 3, 4, 5, 6, 7, and so on. So let's say at index 0, there was a value, and then at index 1 there was a value, and then at index 2 there was a value. Okay, so let me just try to tell you one thing. If there was a value at an index, let's say at index 4 there was a value like this. Okay, now what happens, that let's say this value at index 4 was something like 40, and let's say at index 3 there was a value that was like 30, and let's say at index 5 there was a value that was like 50. This value was 50. So this graph would be something like this, where these are the values. Okay, tell me one thing, if there is a graph, let's say this is the point that I am currently talking about, just keep looking, this is very important. You understand these things that I have drawn, right? I mean that array of 3 is 30, okay, array of 4 is 40, and array of 5 is 50. Okay, let's say there is a point, after this point the graph is increasing. Okay, after this point the graph is increasing, and before this point the graph is decreasing. Okay, what can happen to an increasing graph? Think, if a graph is increasing, what are the things that can happen to it? In the worst case, either it will keep on increasing, or it will increase and then decrease. Can I say that, guys? If a graph is increasing beyond a point, which is happening over here, in the worst case it will just keep increasing, or at some point it will increase and then decrease. Guys, is it right to say or not? Just say yes. A graph which is increasing after a point, either it will keep increasing or it will increase and then decrease at a certain point, right? So if, let's say, the second statement is true, wherein it increases and then decreases, then definitely there will be one peak in the right side, isn't it? Yes, no? And even if the first statement is true, where the graph never decreases but just keeps on increasing, even in that case there will be one peak, and that will be the last element, right? So guys, let's say you attack any middle element, okay, now you see that element which is in the left, that element is smaller. So in the worst case, what can happen, that the graph which is going down will just keep on going down. Will you get to find any peak in this part? Will you get to find any peak in this part? No. It is not necessary that a peak lies. Sometimes you can find, I mean, it can happen that this graph goes like this and then comes back like this. Okay, but in the worst case it can happen that you might not end up getting a single peak, like the case over here. If you have 10, 20, 30, 40 and 50, let's say your mid one was 30. Now you saw that this element is smaller, so going in this part might or might not give you peak, but going in this part will definitely give you at least one peak, because of the reason that I just spoke. Everyone understands that thing, right? Yeah. So now the question becomes very simple. So whenever you are at a midpoint, first check whether this itself is a peak or not. And can you check that very easily? Yes. First just check if a of m is greater than equals to a of m minus 1 and a of m is greater than equals to a of m plus 1. If this condition is true, can I simply return m? Can I simply return m? Right? If this thing is true, M itself is my peak. But if this thing is not true, then how do I decide which side I should go to? How do I decide? By comparing AM with AM plus 1, right? Because if AM plus 1 is greater than AM, then I will go in right side, and if AM minus 1 is greater than AM, then I will go in left side. So the entire concept was just limited to this thing, that if there is a point which is your M, and if graph is growing in this region, then go in this region, and if it is growing in this region, then go in this region. Okay, what will you do if it is growing in both the regions? It can be very much likely, right, that the graph is growing in both the regions. So in that case, what will you do? Can you choose to go in any of those two regions? Yes, no? You can go in any of those two regions, because definitely you will get at least one peak in right side also, and definitely you will get one peak in left side also. Everyone understood the concept behind this? Got it perfectly? How is the approach working? Now this is very important technique, and this has huge application. Okay. So now can everyone implement it also? Can I expect everyone to implement it? Right? You just have to be careful about one thing, that you are comparing AM with AM minus 1 and AM plus 1. So you have to be aware about the what? Indices. So whenever you are at the corner, then you just compare AM with AM plus 1, and whenever you are at right corner, then compare AM with AM minus 1. And if that is not the answer, move left or right accordingly. Cool. What will be the time complexity of this approach? It will simply be order of log n, because every time you are shrinking your search space into half of the initial size. Great. So I think I'll just keep this much for today.